When updating motor control with a variable frequency drive, often called a VFD, while keeping the existing motor, there are important changes to consider regarding overtemperature protection. The updated requirements specify that motors must have embedded temperature monitoring equipment to protect against overheating. This protection should also be independent of the VFD-owned thermal protection mechanisms. Firstly, if the existing motor lacks embedded temperature monitoring equipment, it might need to be replaced with a newer motor that includes this feature. Secondly, depending on the motor type and its condition, it may be possible to repair or modify the existing motor. This involves installing temperature sensors directly into the motor windings or other critical locations within the motor. Thirdly, it is vital to ensure that the chosen VFD is fully compatible with the embedded temperature monitoring system installed in the motor. Typically, this means the VFD must have appropriate input terminals to receive and process the signals from the temperature sensors. There are additional considerations as well. The specific type of temperature monitoring equipment used can vary depending on the motor's design and the specific application requirements. Common options include thermocouples, resistance temperature detectors, often called RTD, or thermistors. It's crucial that the installation of embedded temperature monitoring equipment is performed by a qualified electrician to ensure safety and proper functionality. The VFD built-in thermal protection settings should be carefully coordinated with the motor's embedded thermal protection system. This coordination is essential to provide comprehensive and reliable protection against overtemperature conditions. In summary, when retrofitting a VFD and deciding to keep the existing motor, you may need to either replace or modify the motor to comply with the updated overtemperature protection requirements. Compatibility with the VFD and ensuring the correct installation of the temperature monitoring system are equally important considerations. When dealing with motor protection, several factors come into play to ensure the motor operates safely and efficiently. Understanding these factors is crucial for anyone involved in the selection, installation, or maintenance of electric motors. One of the primary causes of motor failure is overheating. Excessive heat can damage the motor's insulation, windings, and other critical components, leading to reduced performance, premature failure, or even catastrophic breakdowns. Several factors can contribute to motor overheating. These include overloading, which occurs when the motor is subjected to loads beyond its rated capacity. This can happen due to mechanical issues, incorrect application, or changes in the driven equipment. Another factor is voltage imbalances, where unequal voltages are supplied to the motor, causing excessive current flow in some phases. This can lead to overheating and potential damage. Harmonics in the power supply can also create additional heat in the motor windings, contributing to premature failure. High ambient temperatures can reduce the motor's ability to dissipate heat, increasing the risk of overheating, especially in enclosed or poorly ventilated environments. Inadequate ventilation around the motor can trap heat and prevent it from being effectively dissipated. Dirt, dust, and other contaminants can accumulate on the motor's surface, insulating it and reducing its cooling efficiency. Motor protection devices are designed to prevent or mitigate the effects of overheating and other damaging conditions. These devices include overcurrent relays which protect against excessive current draw, which can be caused by overloads, short circuits, or ground faults. These relays typically have adjustable settings to match the motor's full load current and thermal characteristics. Overload relays are specifically designed to protect against prolonged overloads. They typically use a thermal element that mimics the heating characteristics of the motor windings, tripping the circuit if the motor overheats. Temperature sensors embedded in the motor windings can directly monitor the motor's temperature. These sensors can be connected to a protection relay or VFD, which will trip the circuit or reduce the motor's load if the temperature exceeds a safe limit. Voltage monitoring relays can detect voltage imbalances, undervoltage, or overvoltage conditions, protecting the motor from these potentially damaging issues. Phase loss relays detect the loss of one or more phases in a three-phase system, preventing the motor from operating under unbalanced conditions, which can lead to overheating. Ground fault relays detect current leakage to ground, indicating a potential insulation failure. These relays trip the circuit to prevent electrical shock and further damage to the motor. Surge protection devices protect the motor from voltage spikes caused by lightning strikes, switching surges, or other transient events. Selecting the appropriate motor protection devices is critical for ensuring reliable motor operation and preventing costly downtime. The selection process should consider the motor's horsepower rating, voltage, full load current, service factor, and operating environment. Protection devices should be properly sized and adjusted to match the motor's characteristics and application requirements. Regular testing and maintenance of motor protection devices are essential to ensure their proper functioning. This includes verifying relay settings, testing sensor accuracy, and inspecting wiring connections. Proper coordination of protection devices is also crucial. This ensures that the correct device trips first in the event of a fault, minimizing the impact on the overall system. Motor protection is an ongoing process that requires careful attention and proactive measures. By understanding the causes of motor failure, selecting the appropriate protection devices, and implementing a robust maintenance program, you can significantly extend the life of your motors and reduce the risk of costly downtime. When selecting a VFD for a motor, it's important to consider several factors to ensure optimal performance, compatibility, and protection. Here are some key aspects to keep in mind. Firstly, ensure the VFD voltage and current ratings match the motor's specifications. The VFD should be able to supply the required voltage and current to the motor under all operating conditions. Secondly, choose a VFD with appropriate horsepower rating for the motor. It's generally recommended to select a VFD with a horsepower rating that is equal to or slightly higher than the motor's horsepower. Thirdly, consider the VFD control mode. Common control modes include volts per hertz, sensorless vector control, and closed-loop vector control. The choice of control mode depends on the application requirements and the desired level of performance. Fourthly, evaluate the VFD communication capabilities. Many VFDs support communication protocols such as Modbus, Ethernet, and Profibus, allowing them to be integrated into a control system. Fifthly, ensure the VFD has adequate protection features. These features may include overcurrent protection, overvoltage protection, undervoltage protection, and short-circuit protection. Sixthly, consider the VFD ambient temperature rating. The VFD should be able to operate reliably in the expected ambient temperature range. Seventhly, evaluate the VFD harmonic mitigation capabilities. VFD can generate harmonics that can affect the power quality of the electrical system. Some VFD have built-in harmonic filters or other mitigation techniques. Eighthly, consider the VFD ease of use and programming. A user-friendly interface and intuitive programming tools can simplify setup and maintenance. Ninthly, check the VFD compliance with relevant standards. The VFD should comply with applicable safety and performance standards such as UL, C, and IC. Tenthly, consider the VFD manufacturer's reputation and support. Choose a reputable manufacturer with a track record of producing reliable VFD and providing excellent customer support. When installing a VFD, it's important to follow the manufacturer's instructions and best practices to ensure proper operation and safety. Wiring the VFD correctly is essential. Use appropriately sized wiring for the VFD input and output connections. Ensure all connections are tight and secure. Ground the VFD properly to prevent electrical shock hazards. Use shielded cables for motor connections to minimize electromagnetic interference, also known as EMI. Install input and output filters if necessary to reduce harmonics and EMI. Set the VFD parameters correctly for the motor and application. This includes setting the motor's voltage, current, frequency, and speed. Provide adequate ventilation for the VFD to prevent overheating. Mount the VFD in a clean and dry location. Protect the VFD from dust, moisture, and extreme temperatures. Inspect the VFD regularly for signs of damage or wear. Check wiring connections, cooling fans, and other components. Perform regular maintenance on the VFD as recommended by the manufacturer. This may include cleaning, lubrication, and component replacement. When troubleshooting a VFD, it's important to follow a systematic approach. Start by checking the VFD display for error codes or alarms. Consult the VFD manual for information on the error codes and troubleshooting procedures. Check the VFD input voltage and current to ensure they are within the specified range. Check the motor's voltage and current to ensure they are within the specified range. Check the wiring connections to the VFD and motor. Ensure all connections are tight and secure. Test the VFD components such as the rectifier, inverter, and control board. Use a multimeter or other testing equipment to check for proper voltage and current levels. Consult with a qualified electrician or VFD technician if you are unable to resolve the problem. By following these guidelines, you can select, install, and maintain VFD effectively, ensuring optimal motor performance, reliability, and safety. Motor efficiency is a critical aspect of electrical systems, impacting energy consumption and operating costs. Understanding motor efficiency ratings and methods for improving efficiency can lead to significant savings and reduced environmental impact. Motor efficiency is defined as the ratio of mechanical power output to electrical power input, expressed as a percentage. A higher efficiency rating indicates that the motor converts more electrical energy into useful mechanical work with less energy lost as heat. Motor efficiency is typically categorized into different levels such as standard efficiency, high efficiency, and premium efficiency. Premium efficiency motors offer the highest efficiency levels and are designed to minimize energy losses. Motor efficiency is determined through standardized testing procedures such as those defined by the National Electrical Manufacturers Association, often called NEMA, and the International Electrotechnical Commission, often called IEC. These standards specify the methods for measuring motor input power, output power, and losses. The motor efficiency rating is typically displayed on the motor's nameplate, along with other important specifications. Understanding the motor's efficiency rating allows users to compare different motors and select the most energy-efficient option for their application. Several factors can affect motor efficiency. These include motor design, operating load, voltage, and ambient temperature. Motor design plays a significant role in efficiency. Premium efficiency motors incorporate design features that minimize losses, such as optimized winding configurations, improved materials, and tighter manufacturing tolerances. The motor's operating load also affects efficiency. Motors typically operate most efficiently when loaded near their rated capacity. Efficiency decreases at lower loads due to increased losses. Voltage imbalances and harmonics in the power supply can reduce motor efficiency. Maintaining a balanced and clean power supply is essential for optimal motor performance. High ambient temperatures can increase motor losses and reduce efficiency. Providing adequate ventilation and cooling can help maintain motor efficiency. There are several methods for improving motor efficiency. These include replacing older, less efficient motors with premium efficiency models. Upgrading to premium efficiency motors can significantly reduce energy consumption and operating costs. Implementing variable speed drives to match motor speed to the load requirements can also improve efficiency. Variable speed drives allow the motor to operate at reduced speeds during periods of low demand, saving energy. Optimizing motor load by ensuring the motor is properly sized for the application can also improve efficiency. Using a motor that is too large for the load will result in lower efficiency. Maintaining proper voltage and power quality by addressing voltage imbalances and harmonics can also improve motor efficiency. Providing adequate ventilation and cooling to prevent overheating can also help maintain motor efficiency. Regularly inspecting and maintaining motors to identify and address any issues that could affect efficiency can also help. This includes checking bearings, cleaning windings, and tightening connections. In addition to these methods, there are several other technologies and strategies that can be used to improve motor efficiency. These include using synchronous motors, which offer higher efficiency than induction motors in certain applications. Using energy-efficient lighting and other electrical equipment in the motor's operating environment. Implementing a comprehensive energy management program to track energy consumption and identify opportunities for improvement. Educating employees about the importance of motor efficiency and providing training on best practices for operating and maintaining motors. By implementing these methods and strategies, organizations can significantly improve motor efficiency, reduce energy consumption, and lower operating costs. This also contributes to a more sustainable environment by reducing greenhouse gas emissions. Motor maintenance is a critical aspect of ensuring reliable operation, extending motor life, and preventing costly downtime. Regular maintenance procedures can identify potential problems early on, allowing for timely repairs and preventing major failures. A comprehensive motor maintenance program should include several key elements. These include visual inspections, which should be performed regularly to check for signs of damage, wear, or contamination. Look for things such as cracked or broken components, loose connections, and excessive dirt or grease buildup. Vibration analysis can be used to detect imbalances, misalignments, and bearing problems. Periodic vibration measurements can identify developing issues before they lead to major failures. Insulation resistance testing measures the resistance of the motor's insulation to ground. Low insulation resistance indicates potential insulation breakdown, which can lead to short circuits and motor failure. Winding resistance testing measures the resistance of the motor's windings. Variations in winding resistance can indicate loose connections, broken conductors, or shorted turns. Bearing lubrication is essential for reducing friction and wear in the motor's bearings. Regular lubrication should be performed according to the manufacturer's recommendations. Cooling fan maintenance ensures that the motor is adequately cooled. Check the cooling fan for damage or obstructions, and clean it regularly to remove dirt and debris. Terminal box inspection checks the motor's terminal box for loose connections, corrosion, or damage. Tighten any loose connections and replace any damaged components. Overload protection testing verifies that the motor's overload protection devices are functioning properly. This includes testing overload relays and circuit breakers. Motor alignment ensures that the motor is properly aligned with the driven equipment. Misalignment can cause excessive vibration, bearing wear, and premature failure. In addition to these routine maintenance procedures, there are several other best practices that can help extend motor life and improve reliability. These include keeping motors clean and dry. Dirt, dust, and moisture can damage motor components and reduce insulation resistance. Providing adequate ventilation. Overheating can damage motor insulation and reduce motor life. Protecting motors from voltage surges and transients. Voltage surges can damage motor windings and electronic components. Using the proper motor for the application. Overloading or misapplying a motor can lead to premature failure. Keeping accurate maintenance records. Tracking maintenance activities and motor performance can help identify trends and predict potential problems. Training personnel on proper motor maintenance procedures. Proper training can help ensure that maintenance tasks are performed correctly and safely. By implementing a comprehensive motor maintenance program and following these best practices, organizations can significantly extend motor life, reduce downtime, and improve overall system reliability. This also contributes to lower operating costs and increased productivity. When selecting a motor for a specific application, it's crucial to consider several factors to ensure optimal performance, efficiency, and reliability. The selection process should take into account the application's requirements, operating conditions, and environmental factors. One of the first considerations is the load requirements. Determine the horsepower, torque, and speed required to drive the load. The motor should be sized appropriately to handle the load without being overloaded or underutilized. The duty cycle of the application also needs to be considered. Determine whether the motor will operate continuously, intermittently, or on a variable duty cycle. The motor's thermal capacity and cooling requirements should be appropriate for the duty cycle. The power supply characteristics are also important. Determine the voltage, frequency, and phase of the available power supply. The motor should be compatible with the available power supply. The environmental conditions also needs to be considered. Determine the ambient temperature, humidity, and presence of any corrosive or hazardous substances. The motor should be designed to withstand the environmental conditions. The motor enclosure type should be appropriate for the environment. Enclosures are rated according to NEMA or IEC standards, providing different levels of protection against dust, moisture, and other contaminants. The motor's efficiency rating is also important. Select a motor with a high efficiency rating to minimize energy consumption and operating costs. Premium efficiency motors offer the highest efficiency levels. The motor's starting torque characteristics should be appropriate for the application. Some applications require high starting torque to overcome inertia or friction. The motor's speed control requirements should also be considered. Determine whether the motor will operate at a constant speed or require variable speed control. Variable speed drives can be used to adjust the motor's speed to match the load requirements. The motor's mounting requirements should be taken into account. Determine the mounting orientation, space limitations, and any other mounting constraints. The motor's noise and vibration levels should be acceptable for the application. Some applications require quiet operation or minimal vibration. The motor's cost should be considered in relation to its performance and reliability. Balance the cost of the motor with its expected lifespan and operating costs. In addition to these factors, there are several other considerations that may be relevant to specific applications. These include the motor's service factor, which indicates its ability to handle occasional overloads. The motor's insulation class, which indicates its ability to withstand high temperatures. The motor's bearing type, which affects its lifespan and maintenance requirements. The motor's availability and lead time, which can impact project timelines. By carefully considering these factors, engineers and technicians can select the most appropriate motor for this specific application, ensuring optimal performance, efficiency, and reliability. This also contributes to lower operating costs and increased productivity.